Okay. So now let's further define the Gibbs equation. TDS is equal to DH minus VDP. Directly, this comes from this relation. Okay, H is equal to E plus PV, so that you can define enthalpy with entropy. So entropy DS is there, enthalpy is there, PDV is there. Okay, so we can rearrange these equations. So by expressing enthalpy in terms of specific heat at constant pressure, so enthalpy is dH Cp dt. From the very beginning, we have an equation to this kind of representation there. dH is equal to Cp dt. So you can substitute in the place of Cp dt, dH Cp dt. And so look, TDS is equal to Cp dt minus VDP. Now we can divide both sides by temperature T. So here ds is left, and here Cp dt over T, and VDP over T. So again, what we can do, VDP, V is directly from here, V is equal to RT over P. Okay? Because pressure is equal to rho RT, and the specific volume V is equal to RT over P. So I can substitute instead of V, RT over P. So when I substitute, what we can get here is R times dP over P. So this is the final equation. So by integrating this from point 1 to 2, the entropy is change in entropy. But when we perform integration here, Cp ln of T will come, and R ln of P also comes. So for temperature, yeah, so you can perform mathematical integration simply. S1 to S2, ds. T1 to T2, Cp dt T. This is ln type. Again, here, for pressure 1 to pressure 2, point 2, you have dP over P is, it gives you ln. So delta S is equal to Cp ln T2 over T1 minus R ln of P2 P over P1. So that is the entropy change from one point to another. Okay, so otherwise we need to refer the some tabulated thermodynamic function pi. There are actually tabulated functions or tables are there in the books. So for that we can use this relation. This is not pi 2, it is pi 1. Pi 2 minus pi 1 is the integral of Cp dt over T from point 1 to 2. So, okay, once we, this is actually our main formula. And another important formula will come from here. And from that, what we can get is Cp is equal to Cb plus R. Or these are actually Cp and Cv are specific heat at constant pressure and specific heat at constant volume. So Cp minus Cv is equal to R. And then Cp minus Cv over R is equals to 1. So that is simple relation. Okay? So from the ratio of Cp to Cv is called specific heat ratio. The specific heat ratio, which is useful in the most calculations. በጣም አስፈላጊ ከሆኑት ሬሽዮቹ አንዱ ይሄ ነው። ጋማ is equal to Cp over Cv. So, and simply Cp is equals to gamma, we can express it in terms of gamma. So once we know R is constant value, Gamma is something constant for different monoatomic gas or diatomic gas. It is constant. Therefore, we can express Cp in terms of gamma and R only. So, just ይሄ ዲስከሽን እስከሚያልቅ ድረስ አር ለምሳሌ 287 ነው ለጋዝ ጋማ 1.4 ነው here for the diatomic gas the value of gamma is 1.4 so can you please calculate Cp value እነዚህን ቁጥሮች ወስዳችሁ ጋማ 1.4 ነው አር 287 ነው ሲፒ እና ሲቪን ካልኩሌት አድርጋችሁ ወደ መጨረሻ ላይ ትነግሩኛላችሁ ይሄ ክላስ ያልቅ okay so please do it by your hand calculation or using your it is very easy question ይሄን ካልን ደግሞ it is better to go for isentropic process and isentropic flow okay the isentropic process is the process where entropy remains constant. In isentropic process, entropy remains constant. And the Gibbs equation relates the pressure and temperature ratio by the isentropic exponent. So what are those isentropic exponents? Cp is isentropic exponent. R is gas constant. Gamma is isentropic constant. So gamma is isentropic. So the relation between pressure ratio and the temperature ratio are by temperature 2 over temperature 1 the power of gamma over gamma minus 1. Okay, so this is valid for the perfect gas, right? Again, the pressure and the density are related by pressure 2 over pressure 1, which is equal to density 2 over density 1, the power of gamma. So don't forget these formulas. They are very important. እነዚህን መርሳት የለባችሁም ጠቃሚ ፎርሙላዎች ናቸው ብዙ ቦታ ላይ አፒር የሚያደርጉ ናቸው This is pressure and temperature relation. This is pressure and density relation. Pressure and density relation in the isentropic process for perfect calorifically perfect gas application. Okay, so now actually based on what we have discussed, someone can do or perform some example here. It is actually not as such difficult. Anyways, air is compressed from P1. Look, air is compressed from P1 100 kilopascal, T1 50 degrees centigrade, and P2 is 1 megapascal. 1 megapascal means what? 1000 kilopascal, right? Isentropically, the compression is isentropically. Calculate the exit temperature and density of the air, assuming gamma is equal to 1.4 and R is equal to 287. And the gas is calorifically perfect. So what is the solution for this? First, calculate the absolute temperature. At 15 degrees centigrade, the absolute temperature is 288 Kelvin. And then from the isentropic relation, that means we have this kind of isentropic relation. Let me write it. P2 over P1, P2 over P1 is equals to T2 over T1, the power of gamma over gamma minus 1. So from this relation, we can rewrite this equation. Okay, so this equation is directly taking this relation. So that directly gives us the temperature and exit temperature. Calculate the exit temperature, its size. So T2 is the exit temperature here. T1 is already there. Here it is gamma minus 1 over gamma because it is reversed. Okay. When I bring this to this direction, it is gamma minus 1 over gamma. Okay. So first you have to identify this. Then there are two ways. Actually, someone can calculate this one directly. Actually, we can also calculate the density also. Once we know the temperature at point 2 and temperature at point 1, then we can easily calculate temperature, density, other constants. But we have perfect gas law also helps us to calculate. Perfect gas law, that means pressure is equals to rho RT. Equation will help us to calculate rho RT. So pressure at point 1, rho at point 1, temperature at point 1. Pressure at point 2 is equal to, similarly, rho at point 2, temperature at point 2 R. So we directly apply. So this is from the gas law. Therefore, we can calculate density. So using the perfect gas law, we have this kind of 6.267 is the density. And using the isentropic relation of the pressure and the density, that means pressure and density isentropic relation here, using this one, we can also calculate it here. This is same result. Okay, so now let's go to the conservation principle for systems and control volume. So one of the conservation principle is the continuity principle. So the continuity principle states that the mass is conserved. For the conservation of mass, the mass of an object does not change with time. That means the change in mass per time is equal to 0. Okay, so the continuity equation is derived from dm dt for the system is equal to 0. So mass is conserved. And expressing this in terms of integral form of density, mass means what? Rho dV is mass. Mass simply m, just differential mass dm is represented by what? M is equals to, for differential element, density rho. So density is considered fixed density, that it cannot vary, and the dV. So because density is equal to mass over volume, and mass is equal to density times volume. So rho dV is density times volume equation. So just put this into here. So this is the integral form over volume. So this is volume integral. Just to illustrate these thermodynamic systems, actually we have a system, we have system boundary, and we have surrounding, external surrounding, and there are some other mechanisms here. Let me jump it. Anyways, let's come to our continuity equation. M dot means dm dt, which is equals to d, the ddt, actually it is in the differential form, partial differential form, rho dv for the volume integral. So this means by itself, when we using what you call the Leibniz rule, the Leibniz rule leads us from the volume integral to the volume integral of density with respect to time plus the surface integral. So this is the surface on which velocity is pointing perpendicular to the surface, and the surface of the given volume element. So these representations, the mass flow representation, and which is equal to 0. So according to the law of conservation of mass, m dot or dm dt is equal to 0. So this quantity is equal to 0. Therefore, here what you can see is v is the fluid velocity vector. The fluid velocity vector is it is a function of x, y, and x, y, z, and the t in three-dimensional representation. Time is one of the quantity here. Space and the time will come into picture. So v, the vector v can be represented in terms of it is velocity form. So this vector v or the velocity vector v is equals to u in the I direction plus small v in the j direction plus w in the k direction. That means it is just a vector. U is the velocity in the x direction, v is the velocity in the y direction, and w is the velocity in the z direction. So it is a vector. And n prime indicates the unit vector normal to the surface. N is a unit vector normal to the surface. Okay, so rho times v is dot nds is the equation. So this is which is equal to 0 gives us the momentum equation. No, the mass conservation equation. So mass is conserved within the given control volume. Okay, CV is control volume, CS is control surface. The representation CS is control surface, CV is control volume. Okay. Actually, I already shown you what are those control volume and the control surface. Let me go back and show you. This control volume actually. This is a control volume, but if I take a small differential surface here, it is control surface. If I take surface tracing this path, look, let me take a small ds. This is ds. So ds is control surface. And the velocity is always tangent to that control surface. The flow velocity is tangent. So that's why the normal component will come here. Yeah, so based on the above definition or mass flow rate, actually mass flow rate, simple expression for mass flow rate is mass 1 is equal to rho 1, A1, and U1. Density, area, and velocity relation. So this is actually simple representations for the mass flow rate. Let me put it here. So mass flow rate m dot is equals to mass density times area times velocity. This is called continuity equation. So which is constant, which is conserved. And if I divide this quantity by area here over area, it is called mass flux over area. So it gives us what? Rho times V only. Rho times V only. So rho times V is called mass flux. Okay, and m dot is rho times A times V. That is okay. Consider a control volume shown. We have a control volume shown here. There are two inlet boundaries. One inlet boundary here, another inlet boundary here. So through the first inlet, 25 meters per second is the flow velocity in the u direction. U direction means the x direction velocity. Again, the density of this matter entering into this point is 1.2 kilogram per meter cube. This area is given 0.25 meter square, this area 1. Similarly, density 2 is 0.2 kilogram meter per meter cube. Area 2 is 0.1 meter square. So we have all quantities are given here. So what is what we are going to find is we assume the flow is steady and uniform. A steady flow means the rate of change of any quantity is equal to 0. The time rate of change is 0. Okay, that is called. So calculate the exit flow rate from the unknown inlet. So we have 2 inlets and 1 outlet. Look, 2 inlets are there, 1 outlet is there. So the outlet is at point 3. For that, we have to calculate the mass flow rate through point 1, that is rho 1 A1 U1. That gives us 7.5 kilogram per second. Again, the mass flow rate of the second point is rho 2 A2 U2 from the mass conservation. That gives 4.5 kilogram per second. Therefore, the mass flow rate out of the boundary 3 is the sum of the mass flow rate into the boxes or in the 1 and the 2. So m dot 3 is equal to m dot 1 plus m dot 2, which gives us 12 kilogram per second. So mass in, mass out. So that indicates what? According to the continuity principle, mass entering into the system, if this is the system, so some mass entering into the system, m dot at point 1 is equals to mass coming out from the system, m dot out. So this is in. So that is the mass flow rate. That is the meaning of mass conservation. So the next one is momentum conservation. Momentum conservation is also another important. It says what? Force is equal to mass times acceleration is the momentum equation. And that the momentum means what? Momentum P is equal to mv, right? So mass times velocity in the differential form, dmv dt, which is equal to F net. F net is mass times acceleration. Okay, so it can be in xy or it can be in the y or z, it depends. Anyways, this means what? We can put it in the volume integral form, this. So ddt in the volume integral form, rho v dv. V is the flow velocity, rho is the density, because instead of mass, we can put density times volume. Rho is density, dv is volume. Here also, instead of mass, we used, in the place of mass, we used rho dv, right? So ddt is there only. So similar kind of expression. Only v is incorporated here because v is here. Okay, so the addition